number. Guys, thanks for being here. Today we're talking about, as was discussed, predicting blend times in transport of non-Newtonian fluids. Our roadmap for today is pretty straightforward. I want to talk a bit about transport theory. That is how we're tackling these problems using spatially varying LBM-based frameworks that are amenable to local viscosity, local density, and quick changes therein, especially in a non-Newtonian and complex rheology blending process. I'll talk a bit about single fluid non-Newtonian systems. I'll then move on to two fluid systems where we're blending, say, two miscible fluids together with different rheologies. I'll talk a bit about yield stress fluids, which are a different animal altogether, and then move into some conclusions and next steps. Here on my screen is not necessarily a Newtonian system. It's just a low Reynolds number laminar system, kind of highlighting some of the neat structures we can see in these transitional laminar flow regimes, including persistent toroids, pore mixing throughout the vessel, something of a cavern. This isn't a real cavern because this is a Newtonian fluid, but nonetheless, there's this pronounced zone of influence where the fluid is active and where it isn't, as it were. We'll be seeing how these different sorts of structures inform transport blending in both Newtonian and non-Newtonian, as it were, as we go to very different regimes of the Reynolds number spectrum. So let's go ahead and jump into it. I've given this introduction slide before, but I think it's really germane given the nature of what we're speaking about today. When we think about fluid flow and transport, particularly non-Newtonian system, we typically think about some sort of, think about blending thereof. We imagine some sort of vessel. It has some diameter. It has some impeller that's spinning. It has some viscosity that may be a function of space or time or strain. It has some density. And if we think about this thing on the tool on our desk, as it were, we can imagine the impeller spinning, having some time-varying flow field throughout this vessel that is different locations throughout this tank, assuming that it's not just a deep laminar system. We're going to have some time-varying velocity, et cetera, as it were. If we squint in, though, and really look at the system, what we'd see is what's actually doing all the transport, what's actually moving momentum and species through the system is an incredibly large number, Avogadro's number approaching, number of small individual transport carriers, which for fluid systems are the individual fluid molecules, as it were. We would see that in a very tiny differential element of this fluid, a volume even smaller than the Kolmogorov length scale, there would be some fraction of Avogadro's number of molecules inside the system, undergoing all these collisions and bumping and interactions, as it were. These molecules would be moving very fast with respect to any sort of tip velocity or flow velocity inside the system. Moreover, as to be expected, their mean free path and diameter is very, very tiny compared to any sort of turbulent length scale or any sort of physical length scale, as it were. In fact, these things are moving so fast, we'd have a very hard time perceiving bulk flow on top of the fast-moving molecular interactions as we focus in on the individual finite volume of these of this ensemble of particles. If we had a very powerful computer, we could describe the dynamics of the agitated vessel using a molecular description of that system. Said we could describe a interaction between each molecule using some sort of potential function. Maybe for water, you use like tip 5p or whatnot, or maybe a single point charge model, as it were. We could then integrate these equations in motion using MD simulation to predict how these underlying molecular mechanics give rise to macroscopic transport phenomena. And that was my thesis when I was a grad student, was trying to understand how we could link all these molecular motions to macroscopic transport phenomena, things like Navier-Stokes, et cetera, which was great. It was awesome, but it was academic, as it were. But if we really look at this thing, we might realize, and some smart physicists started to realize this, is we don't need to track every single molecule to understand what this micro ensemble is going to do. Said again, if we know these particles are very small compared to this little differential element inside of our vessel, and we know they're moving very fast compared to any sort of advective transport velocity, as it were, we can predict what the distribution of molecular velocities will be a priori, okay? Maxwell did this. We know it's going to be some sort of Maxwellian distribution, and inasmuch as we're at low Mach numbers, any sort of superficial velocity can be treated as a shift in this distribution function about the mean velocity of 0, which is what it nominally is in a closed system. And so again, if we can recast this very large number of particles, even this tiny element, in terms of a distribution function, we can reduce the complexity of the problem by many orders of magnitude, as opposed to modeling trillions of molecules, as it were, in some cubic micrometer of fluid. We can instead describe the net effect of all those collisions, the net effect of all those interactions, as it were, on some distribution function of velocities and collision frequencies, as it were. And this reduces the complexity of the problem dramatically. So carrying on, this transforms the problem from a molecular problem into a statistics problem, where instead of describing the behavior of every molecule and where it's going, how it's colliding, as it were, we're instead describing the probability of finding a molecule at a given location with a given velocity at a given time. Okay, and this was Boltzmann's big idea, as it were. This idea that what transport is. What transport is the time evolution of molecules, as it were, moving throughout the system, building upon Maxwell's hypotheses, and then describing transport as how this probability moves through space and time. So the probability of finding a molecule at this voxel moving to the right is going to be somewhat correlated to the probability of finding a molecule one voxel upstream moving to the right. Said again, we know what's going to happen upstream as a function of what was coming downstream, as it were, in terms of the probability density function. There are some nuances here related to the collision operator, which describes how these probability density functions relax, as it were. But part and parcel, they describe three key effects. We have a streaming effect, where probability density moves from neighboring point to point. We have a collision effect, where these probability density functions relax towards a new equilibrium, which is typically motivated by Maxwellian statistics, as it were. Then we have a post-collide, where this new, freshly collided PDF moves to the neighboring sites. So you can see the molecular origins of this approach, as it were. We have molecules that are moving from voxel to voxel to voxel. And as they move, they're colliding. And if it had a lot of momentum, if it had ballistic transport, it softened and realized some sort of diffuse transport as it underwent a series of subsequent collisions. This PDF describes that same physics. We're describing this probability as it moves, as it washes out due to collisions and diffuses, as it were, due to these collisions of other particles that make this PDF evolve across the system in a manner that reflects what the underlying molecules would do. Okay, and when we do this across 3D space and time, we get a lattice Boltzmann, and at any point inside this lattice, we can recover macroscopic state variables from the integral of this PDF. Said again, we know that density will be the integral over all of the velocities, the velocity distributions at a given location. We know that momentum will be the second moment of the distribution function according to with the velocity being scaled by the PDF. And this locality and time variation is what makes this approach so good for non-Newtonian fluids. Said again, at every one of these points, I know what the velocity is. At every one of these points, I can have my own independent relaxation operator, think of viscosity. At every one of these points, I can have my own density. And so the key point is this: within this local approach, where we're only considering probability density function and how it streams and collides with nearest neighbors, this is a perfect recipe for non-Newtonian fluids, where I need to evoke a spatially varying viscosity that will be a function of local concentration, strain, stress, etc., or even time. So this localized approach and the appeal to local viscosity goes part and parcel with complex rheologies. Now, within the simulation, I showed this kind of grid here. What really drives the ship are resolution and time step. Resolution informing how fine I'm resolving my flow field, how small my box of molecules might be, and time step being how frequently I'm checking for evolution of the PDF through space and time. Let's take a look at resolution first. Resolution informs how much of the flow field I can see explicitly. So in this glass line reactor here, this is just Newtonian water, but I'm going to step through increasing the resolution, and you can see how that changes how finely we can see that turbulent structure, and even the mixing the dye as well. Look at this flow field as I step through higher and higher resolutions. It's getting more and more discrete. I'm able to explicitly capture an increasingly large fraction of these turbulent motions. So as I go to higher and higher resolutions, you can see this flow field becoming more detailed. And yeah, it's not that I didn't know what was going on at low resolutions. It just means I had kind of a crummy representation of the turbulent spectra. As I go to higher resolutions, I can see that turbulent landscape more clearly. And this is going to be very important when we're modeling non-Newtonian fluids wherein spatial variations in strain are going to inform spatial variations in viscosity, which might inspect spatial variations in flow field. So keeping our eye on resolution is going to be important. Again, here's a better example of that. This is just an impulse mixer, but foundationally, the fineness of our grid informs the fineness of the structures we can see. And for strongly non-Newtonian fluids, where we have a strong variation of viscosity with strain, for example, that level of detail is important in getting the flow field right. Let's talk about time step as well, and kind of what we baked into this model when we're building it. I slipped a couple assumptions in there, and now it's time to see what they bring to bear. I kind of just casually said, oh, well, if our molecules are really tiny compared to the finite volume, they're the little ensemble volume, as it were, and that finite volume is really small compared to the diameter, then we can appeal to this Maxwellian statistics. What that really means when I'm saying it is that my Newton number is small. I'm saying here that the molecular mean free path is very small compared to this element, as it were, this ensemble box. So this implies here that I'm modeling a continuum. Said again, a rarefied flow would not generate the same equilibrium distribution function. So I'm going to assume here, moving forward, that our systems are all non-rarefied. Second, this Boltzmann transport equation, as was presented, implied a low Mach number. Said again, when I just said that, the molecules are moving really fast compared to the tip velocity, you wouldn't even be able to see the advection on top of that tip velocity. What I'm saying with those words is that the bulk velocity is very low compared to the molecular velocity, implying we have a very low Mach number. In M-star parlance, this would be a low Courant number, and Mach number being a surrogate for Courant number and vice versa in the numerical scheme. And so foundationally, what I'm talking about today is strictly valid for Mach numbers below like 0.1 or 0.3, whenever you feel like you can tolerate enough compressibility. And importantly, though, outside of just the scheme, we know from fluid mechanics that Knudsen, Mach, and Reynolds are linked, as it were. And so foundationally, if I'm going to be going into low Reynolds number systems, either with a high viscosity Newtonian fluid or a non-Newtonian fluid with a very low shear and low viscosity, maybe near the top of the vessel, I need to keep Mach number low. I need to keep Courant number low in order to satisfy Knudsen condition. So this is not an M-star unique thing. This is fluid mechanics for gases. But at the end of the day, I need to keep my eye on this. If I'm going to go to low Reynolds number, I may need to decrease my Courant number to satisfy Newton number conditions, implying that my flow is non-rarefied. Side note here, since we're talking about history, and I know Amber was going to bring that point up, Mach, his name came up, great physicist, not a great guy in some instances. So Boltzmann's got these like big ideas about atoms and Boltzmann transport theory. And Mach is like just standing up, I don't believe in atoms. I think you're wrong. And even as the pressure came on with Planck and Einstein, Mach's like, atoms aren't real. I don't believe in any of it. Boltzmann took his own life. I mean, there was so much like opposition to his ideas about the molecular nature of the atomic nature of matter and how these atoms move. That like his decade was one of just vicissitude against kind of unacceptance of these new ideas. And it's a pity because like he took his life like just as like Einstein and Planck were like validating everything he said. And so there's kind of two lessons here. One, don't be like a Mach. Like, don't miss out on one of the most important revolutions of physics because you don't like it. But don't be Boltzmann. Like, don't give up. Like, gee whiz. Like, you could be, your discoveries might be some of the most important of the last 150 years. And so I'm not saying we're Mach and Boltzmann here, but I'm just saying like there's a story there that we should kind of revel in. Don't be Mach, but have hope of Boltzmann. Don't miss the boat, but don't sell yourself short. I digress. It's all the Boltzmann street. Maybe got me waxing philosophical. Okay. What's really neat about these types of approaches is the fact that we can model these spatially varying processes. So again, here's just a simple, this is a water system. I'm just agitating it with a pitch blade impeller. And importantly, I have 3 probes inside this system. And I added some dye there. I added the dye at the start of the process. I could have added it later. It's fine. Here I'm illuminating one plane through this 3-dimensional domain and watching both the velocity and the dye homogenize across it. Well, the velocity is not homogenized. I'm just rendering the velocity along that plane. But I'm think of it like a sheet of light going through the center of the tank, illustrating what the concentration is. This is why it looks kind of strange. You'll see this kind of blob hop in and out. is because we're only looking at one sheet when doing our rendering. The simulation was, of course, 3 dimensions. Let's look at these 3 probes in particular. The velocity field, cool, we've seen lots of times before. These probes are kind of interesting because they're showing, and I'm plotting here, the time evolution of the dye concentration at that probe. There's one kind of near the side, near the baffle-ish, not really tucked behind it, just kind of near the baffle. There's one near the bottom of the vessel down here, near the trailing vortex, and there's one at the top of the tank. What's interesting here, and this is not an MSR discovery, hold off on backs in the Nobel Committee. Everyone knows this is run a lab test. But we see here these kind of spatially variations in blend time, as well as temporal variations in concentration. Some of these probes, kind of overshoot, undershoot, and then converge on to their steady state value, that is the mean dye concentration, pretty quickly. Some of them take a while. This top probe, for example, it didn't get within 5% of the mean value until after 80 seconds. This was kind of our rate limiting step here. This was the last part of the region to blend. And so we can characterize both the spatial variations in this blending process, as well as the global effect. I'll play this again just for illustration here. You can see 50 seconds on, 55 seconds on, we're still heterogeneous up here. This is not yet homogenized. This is spinning at about 60 RPM. So it's not unsurprising to see us take like 80 impeller turns, 90 impeller turns for a PBT to homogenize the vessel at this aspect ratio. But foundation after 80 seconds or so gets within about 5% of a steady state value, which is just the mean of the total concentration across the vessel. We can also do a global analysis where I'm looking at the coefficient of variation of dye across the entire fluid. And so at the end of the day, like a coefficient of variation of 10,000 is just silly. It's a silly metric. It's like saying I'm like a billion. It's like saying I'm like 10 to the minus 9 light years tall. It's just like a dumb. It's not even an appropriate unit to measure. It's so poorly mixed that using the degree of mixedness to describe it is just wacky. But as we get down to more of this homogeneous state, the COV becomes a better surrogate for degree of mixedness. And interestingly here is that my COV gets below within a few percent or so, I start to track in to my probe behavior. Like again, I don't know if there's much utility in assigning physical meaning to a dye coefficient variation of 1,000. It's not mixed. And their probes reflect that, of course. There's regions where the dye is not even accessed near the top of the vessel at this 40-second mark. But as we get down to these lower and lower and lower COVs, that link between degree of mixedness, uniformity across the tank, what the probes are seeing makes a bit more sense. It also begs the question of what does mixed mean? Like, it's like, was it mixed then? Oh, it went back out. Was it mixed then? There's a reason why blend time isn't a thing. Mean blend time is, because it's got to be a sampled quantity. What's neat about this approach as well as I go into these non-Newtonian systems is the generality. Again, because the viscosity is local, and the physics are time dependent, it's easy for me to look at spatial variations in Reynolds number and how they inform things like power number in the flow field. Again, this is one modeling paradigm, but it's easy for it to hop between low, transitional, high Reynolds numbers, etc., with no tuning. So again, the Boltzmann transport equation can handle that spectrum of Reynolds numbers without having to kind of futz around with different sorts of turbulence models, because either DNS or LES. That's it. We talked about this in a previous paper, but again, kind of looking at power number as a surrogate for looking at suitability of the modeling framework. Okay, so I've spoken a bit about some of the transport theory, some of the key things I want to look at. Let's jump into the non-Newtonian fluids here. I'm sorry, the non-Newtonian fluids. What makes these fluids so unique, as the name might suggest, is the fact that the viscosity is non-constant. When I have a shear stress in a fluid and plot that versus the shear strain applied to that fluid, if that ratio is constant, I have a Newtonian fluid, right? The viscosity is constant throughout all space and time. The viscosity is not varying as a function of strain or anything else. This rheological expression becomes simple. There'd be no yield stress, and our exponent here would just be 1. And then if we have a stress that's linearly related to the strain, I can conjure up, and any rheologist can conjure up a fluid that has a non-Newtonian viscosity, where the viscosity varies as a function of, for example, shear strain. A power law fluid, one with no yield stress, is going to have some sort of constitutive index and some flow index, which describes how this effective viscosity varies as a function of these fluid properties. We can have fluids with the so-called yield stress, which says that the fluid won't even begin to move until we exceed some sort of critical shear stress. Think of like a ketchup or some sort of toothpaste. But the important point is this, is that our kinematic viscosity, illustrated here, becomes a function of our velocity. And because our Navier-Stokes equations are functions of our viscosity, these two are coupled. Said again, the spatially varying viscosity is informing the spatially varying flow field. And the spatially varying flow field, through the strain, is informing the local viscosity. So these physics must occur at a handshake. We can't just solve the flow field, then put a viscosity on top of it and call it good. This isn't one-way coupling. These all have to be solved in tandem with each other when predicting how these changes in viscosity will inform the changes in the flow field, and vice versa. So this non-Newtonian behavior influences not only the flow field, but the blending profile. So here's a natural solid blend, some sort of yield, no yield stress, some sort of flow index and constitutive index, a lab scale system. We see here, like it's trying to be turbulent in the high shear regions where the viscosity is low. In hinter regions of the vessel, the mixing is quite poor. This does not show this broad turbulent structure we saw in the previous simulations. And that has an effect on blending. Here I'm going to add some tracer particles just to watch it go. And we'll see here as these guys crop in, like a strong variation in the blending profile across this tank. Look at the top. It's just this laminar ribbon that's moving around the vessel. As we get near the sides here, we get some echoes of a toroid or some sort of transitional flow regime. Down in the trailing vortex at the bottom half of the tank, we get decent turbulent flow. But within this non-Newtonian system, we're running the whole gamut of Reynolds numbers. And we're seeing a whole spectrum of different mixing characteristics. We see, again, these kind of laminar lines up top, the lamella of the flow near the top of the vessel. We see a transitional effect here with the beginnings of a torus or other sorts of transitional flow structures. And down at the bottom, we see a pretty well-defined turbulent flow and turbulent mixing pattern. But again, this is where the locality and time-dependent coupling come into play. To get this profile right, to get this mixing profile right, you've got to get that spatially varying profile, velocity profile appropriately modeled. We validated this quite a bit. We've published on this and also presented on it, looking at how different sorts of natural solid blends ultimately inform the blend time. One thing to note here, and I make this point quite emphatically, is that, again, blend time is not a thing. Mean blend time is a thing. A blend time variation and standard deviation is a thing, but especially in these laminar flow regimes, you'll see measurements at the same Reynolds number. And again, this was different fluids, even for the same fluid though, where your blend time can vary by 25, 50% between runs. That's not a problem. It just means that the particular nature of the flow field at the instant in which you added the dye may have enabled a faster blend time or a slower blend time. And so oftentimes repeat tests, both within simulation and an experiment, in terms of injecting the dye at different locations, or even considering injecting the dye at different times, can help you sample those variations that come from the non-constant flow field. And as I showed before, the ability to capture these toroidal structures that exist even in non-Newtonian fluids with low Reynolds numbers is an important hallmark of these local and high density approaches. Said again, if we don't have the resolution sufficient to see this gradient, we're not going to capture, we're going to bleed out, we're going to be overly diffuse. Our numerical diffusion will trump the day. But if we have a resolution and temporal fidelity sufficient to capture these flow fields, we can see persistent and long-lasting toroids across the vessel. Here's another picture of that across 2D. Here I'm showing, again, that kind of the dye going through a lit up plane, and I'm showing where these particles are landing as they were added to the dye. And so foundationally, again, with an approach like this, we can see these persistent time-dependent structures as they fluctuate around that exist in these low Reynolds number regimes. Now, again, this was Newtonian, but this comes up all the time when blending non-Newtonian fluids and seeing some of these persistent toroid structures. And what this means is that blending looks very different. I'm going to harp on this in a few minutes, but blending in these systems is very different. It's very different compared to blending in turbulent systems. It's much less of an engulfment process and more of a diffusion and almost like a melting process, as I'll illustrate momentarily. Now, Rod, just about 300 points across the vessel. We can talk about that later. But yeah, I'll just answer that question now. But I shouldn't have jumped ahead. But it's kind of cool to see like these persistent dead zones or toroids that just aren't gonna blend. And people have come up with all neat schemes. Maybe they'll do like a time-dependent impeller speed. Maybe they'll turn it on and turn it off and turn it on, or vary the speed as it were to try to break up these toroids, which is a real problem in blending. But it's neat to be able to predict them, and again, it's made possible by the fact that we're seeing such tight control over numerical diffusion. The same rules of the road still apply. Okay, just because we're modeling a non-Newtonian fluid doesn't mean that conservation of energy goes out the window. It's still true. So here is a Russian agitated vessel, and here I'm showing, for example, that conservation energy still holds up, at least within 10% to the degree of our numerical precision. On the blue line here, I'm showing the power in that comes from the torque on the impeller times the angular velocity. On the black line here, I'm showing the energy dissipation. That is the volume integral of the energy dissipation at each point. Those are wholly independent calculations. But importantly, the code is doing a pretty good job within, I'd say like 5% or so. They're showing that all the energy coming in is being captured in the turbulence model when trying to predict the energy dissipation across this vessel. And that's an important point and a subtle point. If you're not getting EDR right, it means you're not getting strain right, because EDR is the double dot product of the strain rate tensor. So if you're not getting strain right, you're not getting your viscosity right. If you're not getting your viscosity right, you're not getting your flow field right, okay? So like you can hang a lot on EDR, the conservation of thermal energy. And again, and importantly, if you can't do this in your simulation, you need to scratch your head a bit, because foundationally, if you're hanging your hat on a non-Newtonian fluid, which is typically evoking a strain rate dependence, but you can't get EDR right, some plugs aren't fitting together, okay? Likewise, you need to keep an eye on resolution for physics, as it were. So here is just another blending process, but again, making sure that as my resolution goes up, I'm not getting stark changes in blend time. Again, best practices still apply. Keep an eye on time step. Keep an eye on resolution. Sensitivity studies. The rules don't go out the window once you change the rheology. All these physics still apply. Let me keep on it here. Okay, so I've spoken a bit about single-phase non-Newtonian systems, and I sprinkled in some Newtonian low Reynolds number, because the toroids are come up a lot in the non-Newtonian systems as well. We talked about spacing resolution. Let me make sure I kind of made that point. Conservation laws still apply. I want to harp on that, and the importance of checking those things. Because foundationally, if we're going to stand in front of this analysis, right, we better make sure that at least our conservation laws are satisfied. At least mass is conserved. At least momentum is conserved. At least energy is conserved, as it were. If those things aren't being satisfied, it's hard to build a more complex model on top of that. And just double check. So for energy to be conserved, you check it by looking at power in minus power out. For momentum to be conserved, you look at the torque on the impeller and compare that to the torque on the vessel, right? And if that doesn't match, you got a momentum problem. For mass to be conserved, you just got to make sure you're not aggregating mass throughout the simulation, as it were. But LBM or any methodology, if you're not checking those three boxes, I don't know, it's hard to hang a lot of more complex physics on that if you can't get those things kind of down pat. Let's look at our two fluid systems. Maybe editorialize, but I think it's true. In fact, I'm pretty firm in that. Let's talk about the two fluid systems here. Before I talk about the complex rheology, let me introduce this concept of just density alone, because a viscosity, a strain rate dependent viscosity can matter, but if you're in a very turbulent regime, it may not be the driving factor. Said again, if you're in a Reynolds number above 100,000 and your viscosity is changing by a factor of 2 due to strain rate effects, you're still fully turbulent throughout that vessel. Your blend time is going to be probably well correlated to standard single fluid turbulent blend time correlations. And so the non-Newtonian behavior can matter if you're in a transitional laminar flow regime. It may not in a turbulent system. But some effects that do matter across regimes can be density stratifications, which are kind of the handshake or the other side of a viscosity variation. Let me illustrate that here even before I get into the non-Newtonian stuff. Here's a fluid of low density stacked on top of a fluid of higher density. I have the same viscosity. They're both water-like. It's just the fluid on the top has a density of 900 kilograms per meter cubed. The fluid below has density of 1,000 kilograms per meter cubed. One way to characterize the magnitude or the effect of these density differences is to look at the Richardson number. This is relating the effective density stratification to the effective inertia here, as characterized by the impeller speed. And so foundationally, a high Richardson number implies that the density stratification and the effects of buoyancy are going to be large compared to inertia. Okay, Richardson number isn't great because the position of the impeller is not included in it unless you maybe bake it into one of these height scales. And so you can have two systems with two similar Richardson numbers with very different flow fields should the fluid interface go right through this impeller region. But nonetheless, it's a useful metric for characterizing density stratified systems with interfaces not directly agitated. And here I'm plotting how blend time varies as a function of Richardson number. And these are all in the fully turbulent regime, bear in mind. So this tau here, this is the non-dimensional blend time as normalized by the single fluid blend time. So tau of 1 implies that a single fluid system would have homogenized in that time. Make it for this Russian system, make it 50 impeller turns, 40 impeller turns, as it were. A tau of 2 means there's been like 80 impeller turns. It's been twice as long as it would take for a single fluid system to blend. So when my Richardson number is low, implying that my density difference is small relative to my inertia, my blend time, not too far off from single fluid, right? Not too far off. Order of magnitude consistent, okay. Maybe it took me 25% longer, but foundationally, when density effects are small, I blend in a run in a time that's reasonably consistent with a single fluid system. Richardson number 1, it looks a bit different. Like here, I'm kind of eating away. I'm not engulfing the second fluid anymore, as I am at the lower Richardson number or single fluid systems. I'm kind of eating away at that. I'm kind of corroding away at that lighter fluid. And it still blends. It took maybe 3 times longer than the single fluid system, relative, as normalized by tau equals 1. But so we're feeling some of the density effects, but it's still homogenized. Now imagine a Richardson number of 10, which isn't outlandish. Like this isn't blending in the canonical way anymore. This is not an engulfment. This is not even like a fast erosion. This is almost like a melting process where I'm kind of sweeping away the secondary fluid from the interface and drawing it down into the bulk phase. Like this blending process is different, right? This blend time is going to be orders of magnitude longer than what we would see in a conventionally agitated single fluid system. And that's not even viscosity talking. That's just density differences informing this long blend time. And we've talked about this in previous papers, as it were. And so that's kind of a precursor that, yeah, Newtonian, or rather, complex rheology is great. Complex rheology can inform blend times, but don't forget about the heavy hitting effects of density alone, which, again, before we even introduce the complex rheology, density is causing the blend time to exceed single fluid expectations by orders of magnitude, okay, as would be realized in high Richardson number systems. This has to go like 50 before it blends. Let's look at this in action in kind of a real common application. Let's look at a dilution process. So here are kind of the rules of the road. I borrowed this from a paper written by Eli Lilly. They're a simple problem where they're trying to blend some, or rather I should say dilute, some sort of protein surrogate solution. So here they have some sort of CMC, carboxymethyl cellulose. It's going to be diluted with some water. The CMC solution has a higher density than water. It's stacked up high. About 80% of this vessel is a CMC solution. They've got some constant viscosity water on top, lower density, constant viscosity, a given diffusion coefficient, and they're going to be agitating it, stirring it with some sort of, A310 hydrofoil, a given diameter. This impeller speed will vary across cases, but foundationally, the question is this, is how long does it take to blend? Okay, how long does it take to blend? And again, the answers are going to surprise us because these blend times are ridiculously long. And these are not predictions, these are measurements. These aren't like some sort of like weird simulation gave some weird result. Like this was measured. Like if this were a canonical single fluid system, we would expect maybe, I don't know, 100 impeller turns, 120 impeller turns, just shooting from the hip. Like if I were on a desert island and someone said, you're off, if you give me a good expectation of how long this impeller would take to blend this tank, I'd say 120 impeller turns. Where's the lifeboat? Okay. But realistically, these things are taking thousands of impeller turns to blend, okay? Which is not anomalous given the physics, but certainly very different from what we'd expect if this were all, for example, water. And the question is kind of why, and can we change that? But foundationally, that's the stark headline of this simulation, is that blend time takes super long, is what the headline says, compared to what we might expect from literature correlations. So let's go into it. Now, if we're going to model this and understand it and engineer it, we've got to get the rheology characterized. Okay. Now, luckily, CMC is a pretty common. Is anyone else hearing me say Christian McCaffrey? But either way, a CMC is a very common fluid, and it's been well characterized. As a consequence, there are literature correlations that describe how the viscosity varies as a function of shear rate. And this stuff's kind of wicked because it's modeled as a cross fluid, okay? And it shows some pretty interesting effects as a function of shear rate, right? At very, very low shear rates, at very high concentrations, it can thicken with shear rate. And then it starts to thin with shear rate, as the shear rate, I should say. Now, this is a complex rheology, but happily, we're focused down here. Remember, our maximum concentration was 0.6%. And as it agitates, it's going to become more dilute. So you don't have to worry about these kind of crazy effects over here. Moreover, our strains are not going to get below 1 reciprocal second, a fraction of a reciprocal second. We're going to be pretty well limited to this kind of one reciprocal second and above, up to maybe, a few hundred reciprocal seconds. So foundationally, our system is in this space here. And so we can look up from this correlation what we think the viscosity of 0.6 should be. But we don't just need 0.6. We need to understand how this viscosity varies as the fluid dilutes and mixes. So what we really need to do here is look at kind of how our viscosity, how this cross relationship varies as we add more and more water to the system, making it more dilute. If we squint at this, we realize that these three lines, 0.6, 0.4, 0.2, they're really self-similar. That is because we're operating over a relatively narrow regime of surrogates, we can anchor this variation in viscosity primarily to the change in mu naught, right? That is, if we know what mu naught might be, if we know what the concentration is and the variation of mu naught with that concentration, we can do a pretty good job of predicting what the shape of this profile is going to look like at higher strains. So again, it's just shifted by the viscosity at zero shear rate, okay? The zero shear rate viscosity. And so again, that's an assumption we're making to make this model easier to handle, but it's not it's not a bold assumption. It's a reasonable assumption given the linearity of the response here, even the semi-log plot, with due to variations in concentration at this very low CMC concentration. So what does this look like? We have some sort of a linear mixing rule in this low concentration. As you get to higher concentrations, linear is no good. But at low concentrations, you might be able to get away with it. What's it look like in the model? Well, here it is. We have some model here. We've got some cross-model parameters describing the viscosity of the CMC fluid. Then we have some mixing rule down here. There's the viscosity of the cross fluid. Here's the mixing rule. And importantly, we're looking at the viscosity at each point inside this domain. Remember what I was saying earlier, is every single lattice site is seeing its own viscosity as a function of its own shear stress and its own water concentration. And it has to be that way, okay? We can't, and I'll speak to this momentarily, we can't apply uniform viscosity to the system and capture the effects that were observed experimentally. We've got to get the rheology right to get that long blend time as observed. So again, that's the important point. This is not a global viscosity. This isn't some sort of like gray box mixture mean viscosity. We're actually capturing how the viscosity is varying at each lattice site over time in response to strain as well as concentrations. And here's what this looks like. Here's a snapshot of the system after maybe a few impeller turns, maybe I don't know, 10 impeller turns, I'll guess, for the system. Our water concentration, high. We're getting a little bit of entrainment down below, but a layer on top. This, you could think of this as being our density mapping as well. Here's the local strain rate. We get lots of strain right around the trailing vortex, the impeller, that makes sense. And lo and behold, we get lots of variations in the viscosity, right? We have a lower viscosity immediately in the tip. We have our water-like viscosity in the wall up here. And between these two, some sort of blend. This right here is primarily a visualization artifact as the color map is trying to step between these two viscosities. Realistically, the interface is far sharper in the code than will be rendered in this image generation here. But the important part is that I have a spatially variant viscosity that is low near the impeller to high strain and higher viscosity up top near the interface. Here's a very fast moving system, but it'll illustrate some of the key features of this flow. Is that I don't blend, I kind of erode away. And this is for a fast moving impeller, so this is not the simulation result here, but the physics are somewhat similar. Watch me kind of melt away that top layer. It's not an engulfment as much as it is an erosion of that top layer. And when we model this, we can see that, yeah, we can recover these, thousands of impeller turns long blend times. That again, the code might have landed around 2400. Measurement might have given us 2300. Yeah, 2300, I'd say. Not bad at all. That's really good. That's good, but also like a very fortuitous result. Had we changed our viscosity or by some even small fraction, or changed maybe the position of the impeller by some small fraction, we might have shifted this blend time, I don't know, a couple hundred seconds one way or the other, just because it's a mean blend time, not a specifically quantified value called blend time. But to be sure, getting this, the headline is this thing takes thousands of impeller turns to blend, and we can predict that it's very different from the single fluid system. And here's why viscosity matters. So if I just use the constant viscosity model, if I just assume, well, let's just assume the fluid has the same viscosity as the viscosity near the impeller, as it were, we get the wrong answer, okay? We get the wrong answer. We blend like in 40% of the time, okay? Our power number looks the same because the power number of the impeller, as it was spinning in that cross fluid, it saw a fluid with a viscosity of about 50 centipoise. So when we use a single fluid with that viscosity, we're going to get the same power number, but the blend time's wrong, because we're not capturing the low viscosity that is realized up near the interface. And we can do this across a few different impeller speeds and do a pretty good job here of matching what was measured experimentally. In terms of increasing our impeller speed to decrease our blend time. What's really noteworthy here, though, is just how long these blend times get. In turbulent systems, blend time is oftentimes correlated to number of impeller turns via some cofactor. Okay, and that's why I kind of use this, 50 impeller turns, 80 impeller turns, 120 impeller turns. If you're in a turbulent regime, it's easy to characterize blend time for a given topology in terms of impeller turns. And that's a helpful way to guess blend time for different impeller speeds. Here we're seeing as we go from like 300 to 500, the blend time goes for like 100 to 800. Okay, so we are way beyond this turbulent expectation regime and into a system and into a regime where the blend time is entirely a function of the rheology. And we can't just use this helpful little impeller turn mapping when estimating blend time across this system. Okay, let me get this back up here. Okay, so we've spoken about transport theory and the importance of this locality in predicting spatial variation of viscosity. We spoke about non-Newtonian systems in general and some of the rules of the road as related to energy dissipation, momentum conservation, resolution. We spoke about some of those complex structures that can appear and the heterogeneous mixing profile that is characteristic of these systems. We have laminar mixed at the top, transitional in the middle, turbulent down below. Again, to get that right, you've got to be able to capture the spatial variations of viscosity and underlying flow field and how they're coupled. We spoke about two fluid systems, and I emphasized that density stratification effect. I don't think it gets enough play, especially in turbulent systems where people get really focused on viscosity for good reason. But if you're fully turbulent, changing your viscosity by 30% isn't going to change your blend time that much. But density stratifications, they can persist. It's important to recognize those and quantify those and see if they're not having an effect on blend time, perhaps more so than the non-Newtonian nature of the flow field. As a last point, let's talk about yield stress fluids. Okay, so yield stress fluids are just different. Okay, here I'm looking at, let me explain what a yield stress fluid is. A yield stress fluid is a fluid that doesn't move unless the shear stress exceeds the applied shear stress exceeds some critical value. And let me illustrate this within the context of like a pipe flow problem. So here is, for example, a flow through a pipe with a very low shield stress. In fact, I'd say negligible shield stress. But foundationally, we have some sort of parabolic velocity profile that's characteristic of these laminar pipe flows. We see a velocity of 2 at the center line, 2 over the mean, I should say, and a nice convergence is 0 at the pipe wall. This obviously being a 10 centimeter diameter pipe. So what I see here is that if my yield stress is very small, in fact, negligibly small, I recover this well-defined quasi-parabola. As I start to introduce a yield stress, as I start to get one of these yield stresses in here, I begin to get plugs. That is, there are certain regions of the pipe where the fluid does not exhibit this characteristic quasi-parabola. Said again, we know that shear stress is highest near the wall. If you remember that just from quasi-flow, it's going to be some V-shaped profile that's zero at the center line and high near the wall. So there's going to be some points at which that shear stress can't overcome the yield stress of the fluid. And that point obviously pushes out as our yield stress gets up. Look at the yield stress of 10 versus 100. So as our yield stress gets higher, an increasingly large fraction of the system will be subject to this plug flow. As the yield stress gets lower and eventually down to zero, we recover a quasi-parabola throughout. Now, there are ways to analytically predict what this plug is going to look like. There are ways to analytically predict the velocity profile in the regions where the fluid is flowing, as it were. And those things are a function of this sort of plug radius, which is related to the yield stress, as you might expect. So here's just showing some simulation versus experiment. Even in pipe flow, we can model these plug flow systems reasonably well. Simulation shown in dots, exact flow shown in lines. And it's important to recognize that these are the hallmarks. There's going to be a region where fluid just isn't flowing. So what does this look like in an agitated vessel? Well, what it looks like is this. And here's just a kind of a standard lab scale system, 15 centimeters diameter. You can go as big as you want to, of course. A given impeller speed. It looks like this. We get a cavern. We get a region where the fluid is mixing and fluids are well stored inside that cavern, and a region where it isn't. Okay. And I want you to see the parallel between this sort of physics and this physics. So just as for the pipe flow problem, there's a region where fluid just isn't flowing. It's being advected due to the motion near the wall, I should say, but there's a plug. Here we have the same general idea. There is a donut here, a toroid, where the fluid is going to be well stirred, and a radius beyond which where the fluid won't. And this is a pretty modest yield stress, I should say, just two or three. You can have fluids much higher ones. They can be 10 or even 50 in some sludges. And so foundationally, the mixing here is not about trying to get this fluid agitated up here. Let me replace that. It's less concerned about trying to get this fluid entrained. It's more about trying to get this cavern big enough to encapsulate the entire vessel. So this isn't a mixing problem in the canonical sense about trying to erode away a layer and train down some sort of dye. In this problem, we're trying to get this zone of action, this region of interest, large enough to envelop our tank. And the largeness of this mixing zone, as it were, that's characterized by the cavern, is a function of the yield stress, the impeller speed, the number of impellers, the power, etc. So again, what this looks like, and there's been some really, really cool work on this, using X-ray imagery and other ways to characterize these caverns, but we have a zone of influence and a radius of that zone. And there are a couple different ways that people try to characterize these, either using like a toroid model or some sort of radius of influence model. I'll speak to this momentarily. What they're all telling us is that the extent of this zone is a function of the rheology and obviously the impeller speed and size. And mixing happens inside of it. Mixing doesn't happen outside of it. So if we want to mix this vessel, we need to get this zone of influence to extend to the walls of this vessel. And we can do a pretty good job, and we wrote a paper on this last year. We can do a pretty good job of predicting cavern size and comparing that cavern size against some kind of off-the-shelf correlations. And again, very smart people have studied this and have used a variety of frameworks and experimental techniques to validate these correlations, but tried to estimate what the toroid or what the cavern size should be, those different subscripts for a reason, as a function of yield stress operating conditions. And foundationally, we can predict those pretty well, I'd say across impeller speeds. And importantly, you get to a point where you hit the wall. And that then defines the maximum size of the cavern for a given system. Okay, so again, not much more to talk about here, I should say, for the yield stress fluids. We can handle them, they're well supported, but it's kind of a tricky problem because it's a very different mixing problem where you're not trying to entrain a fluid in the classical sense or even erode away at a fluid. You're trying to swell this region of interest until it contains enough of the tank to blend. And this one I'm showing here, it's not happening. It's not happening here. This is meant to be a hyperbolic illustration here, but it's not happening. Okay, conclusions. This localized approach, I'd say LBM in particular, is very well suited for time-dependent spatially flows. Why? Because each cell is calculated independently, we can use the local strain. We can use local species concentrations to calculate some sort of net rheology and predict how that rheology is going to form flow, right? And this has to be solved in tandem. You can't decouple velocity from rheology in a non-Newtonian system. They're coupled in solving Navier-Stokes. And this is the landscape, again, presented by non-Newtonian fluids. The rules of the road are very similar. Keep an eye on resolution and keep an eye on time step. The resolution informs how much of the turbulent spectrum we're seeing explicitly. The resolution informs how fine we're seeing this viscosity field. The resolution informs what fraction of the turbulent structure is going to form the viscosity. Likewise, you need to keep an eye on time step. This is not an M-star thing. This is a fluid mechanics thing. Is that if you have a very low Mach number system, you need to have a very low Mach number in order to realize a low Newton number. Newton, Mach, and let me jump. I'm sorry, I just slipped my mind. Newton, Mach, and what's the third one? Why am I forgetting all of a sudden? Someone help me out. Rarefied Mach number, Reynolds number. Thank you. Yeah, Newton, Reynolds, and Mach are correlated. Thank you so much. I don't know why I slipped my mind. Reynolds is a good guy, but it's either way. They're correlated. And so when you're running a low Reynolds number system, you've got to keep your Mach number low in order to satisfy the low Newton number condition. And all these rules apply about conservation laws. Energy is still satisfied. Mass still satisfied. Momentum is still satisfied. Just because the rheology is changing doesn't mean conservation laws break down. Two fluid models are very much in play. Keep an eye on density differences, potentially even more so than rheology. Again, in a fully turbulent system, the rheology and variations might not have a big effect, but density, as characterized by the Richardson number or some Richardson number adjacent quantity, can strongly inform blend time and entrainment. Custom viscosities can be incorporated. That's great. That's well and good. And the blending may look very different from single-phase systems. It might be orders of magnitude longer. And recognize the uncertainty in these guys. Again, even in these repeatable tests, it's not uncommon to see variations of 40% between two blend times. And I've got, you can look at one of the theses I'd like to look at is one by Aaron Strand, the University of Rochester, or maybe it was RIT, where he just systematically examined blend times in the same vessel over and over and over again, and shown that depending on the universe felt that day, the blend time could vary by a factor of 2x, given the same impeller, same speed, same injection profile, same dye, just because, again, some butterfly flapped its wings in China. Lastly, beware of yield stress fluids. They're there. Okay, they're here. We can't mix them very well. We can mix them inside the cavern, but the mixing process is informed by how far we can stretch this cavern, not necessarily entraining fluid inside of it, as it were. So again, there's good literature correlations we can point against, but foundationally, we're going to blend inside it, not outside it. As a physicist, we can code pretty well. Okay, guys, we covered a lot of ground. I'm happy to take some questions. Some percolated through. Thank you for being here. I very much appreciate your time and attention, and I'll take any questions that come through, Amber. Fire away and let me know what people are saying.
Okay, yeah, we have one question. We've gotten a couple comments on it, but I think I'd love to pass it by you and get your take on it. Here is the comment. This is this is with regard to the two fluid systems and the density stratifications. This is a pathological design. Why model it? We know how to fix it without CFD. You just put the turbulence where you want the action.
Yeah, I agree. Great. A lot of time, the process engineer isn't involved in the topological decisions of the system. And in fact, you get funny quotes. It's like oftentimes the process engineer is the last person to make a comment. And so you have some sort of system, as it were, some sort of retrofitted or some sort of vendor supplied system which doesn't match the configuration at play. And so, yeah, some of these are pathological. And I think I'm trying to, I don't know who asked this, but this is the fact of the matter, is that oftentimes the processes are squeezed into equipment as opposed to the equipment being squeezed into the process. And so, yeah, I'd say that this is not, although pathological and poorly designed, I'd say it's routine. At least what I see coming across my desk, at least people in biopharma. But great question. But yeah, and to that
Right.
point, put the turbulence without the mixing. That's why in this paper, we're like, hey, if you want to blend this thing, put the impeller near the interface. Add the that idea of putting the turbulence where you want it is like the principal question in this. I'll find out who asked that question. But that's
It's
exactly
Art Etchels.
Oh, Art Ectels. Oh, okay. Well,
Ectels.
yeah, that's a great question. But yeah, the point of putting the turbulence where you need it is like, yes, that's correct. But unfortunately, sometimes what the vendor gave us or what the facility has might not allow us to do that. And you know that, Art. Maybe ask that question to make a good answer.
Yeah, next question. Can cavern size be simulated for solid liquid systems using properties of each phase, or would a substitute for each phase be required to model as a single shear thinning fluid?
Okay, so to be sure, everything I've spoken about today has been related to fluids. Okay, when I'm solving when I'm using the Boltzmann transport equation to approximate a solution to Navier-Stokes. Okay, rather I'm solving BTE in a way that satisfies Navier-Stokes. And so when adding a yield stress is a modification to the Navier-Stokes equations, you essentially just give part of the fluid a super high viscosity to model the solid, as it were. But realistically, we're not modeling a real solid. We're just modeling the fluid with a infinite viscosity in regions where the shear stress is below some critical value. When modeling solids, I get a little bit of chest tightness because foundationally, our governing equations of motion do not assume any sort of like linear elastic constitutive model. Okay. And so I don't know how well we can model a solid liquid system unless it's like, if there are solids dispersed there, that might be in play. If it's like a CFD DEM, as we discussed in our last seminar. But I will say this, I don't know yet, but we are kind of hardwired towards solving Navier-Stokes. And so the solutions we solve are Navier-Stokes adjacent. And I wouldn't feel comfortable going into like a solid mechanics system with this paradigm yet.
Okay, next question. And this was a question put during the conclusion. Where are the cliffs in this approach? For example, LL.
Liquid. What does LL mean? Liquid dispersion or?
Maybe Suzanne Cresta, you want to clarify that? In the meantime, one more question. Oh, yes, liquid. Yep.
Couple approaches. With any numerical approach, we've got to keep our eyes on things like numerical diffusion and long time step simulations. Imagine you have, and we're not talking about liquid dispersion, even just miscible liquid systems. If we don't have numerical dispersion on a very short leash, our numerics will homogenize the fluid before the physics will. And so we need to make appropriate use of a flux limiter and small time sensitive resolution to keep that under control. If we have immiscible fluids, and that's for a future seminar here, we may break those structures up into objects that are too small to be seen by the lattice. That requires Eulerian Lagrangian conversion. That's, again, a future talk. But I'd say for the two miscible fluids, the cliff is going to be numerical diffusion, should you have a very slow bending process. For immiscible fluids, I think it's going to be an issue with rendering very small droplets and some conversion thereof. No drops of suns. Okay, yeah, thank you.
Okay, one last question, I think. In a practical sense, do these simulations, which have varying fields of viscosity as a function of local velocity and shear, take substantially more time to run than simpler mixing studies?
Great question. I understand what you're asking.
Okay.
Not necessarily from a competition standpoint, not necessarily. I mean, yes, there's more work that has to be done by the code to calculate the local viscosity at each time step, but like it's not going to sink the ship in terms of running the simulation. The costs of doing that calculation at each time step are not huge. It may be a 5-10% haircut on overall run times. Awesome.
Okay, well, yeah, that brings us to the end of the questions.
Thank you, guys. This will be available online. Reach out as needed, and we'll take it from there. Thank you so much.